If I were to characterize what we did on Friday, I would say it was hopefully to a large extent a review of what you learned in pre-calculus. So, and I think some of what we're going to do, you might feel that way too, but we're starting to get into what might be considered new stuff, perhaps. We're going to take first the notion of a geometric series and try to generalize it a little more broadly. So take, for example, a very basic geometric series and its sum that we would have encountered. I think we did that exact problem on Friday even, actually. So no surprise there at all. So consider that series, and then we want to ask, what would happen if you replace this with all of the 1/2s in this expression with x? Or how about r, whichever, some letter, right? Replacing that with a letter, again, at this point is like, okay, well, that's not a huge surprise. But when you stop and dwell on what we're actually trying to say here, that this, on the left, this polynomial expression, it's not really a polynomial, it's this infinite polynomial expression, equals this rational function, it actually does give you a little bit of pause to think that this actually equals, like that equals sign belongs on the page is a little bit startling when you actually start to dwell on it. So this is true, and this equality does hold, of course, subject to the requirement that x is a number between negative and positive 1. We might call that, for this function, the interval of convergence. And this is our very first and most basic example of a power series. And a power series is, well, I'll define it more clearly on the next slide. It's a series with powers of x in it. That's a quick way to say it. We'll have more complicated power series. Like I said, this is the very first and most basic example of a power series. I don't know. Does that give anyone else pause? Is that startling to anyone else that this expression on the left would actually equal the expression on the right? I think that's hard to stomach, that we have some infinite polynomial that equals a rational function. For example, it's even hard to see that this has a vertical asymptote at x equals 1. This infinite polynomial has a vertical asymptote at x equals 1. I mean, this is just hard to wrap our minds around, that this function on the left and this function on the right are the same for certain values. Oh, here we go. So this is the more complicated way of saying it, but let's just make sure we understand by a power series, we just mean some constant plus some constant times x plus some constant times x squared, etc. We call that maybe a power series centered at 0. So we'll focus on that first. Now keep in mind that many of these C0, C1, C ends could be 0 too. That's completely fine too. Some of those constants might zero out. That will happen. But the point is, if you have something that can be written in this way, you have a power series. If you have something that can be written as some real number plus some real number times x plus some real number times x squared, etc., then you have a power series. And more specifically, a power series centered at 0, a power series could also be shifted left or right by an amount a, in which case we might call that a power series centered at a. And so really, we're just a tad more flexible than we first came out and said. It's fine if we have powers of x minus or x plus a number. We consider that a power series too, given that all that is just a shift left-right on the other one. And there are lots of infinite series that are not power series. They have to be able to be written in one of these forms. Jack. Is every geometric series a power series? Yeah. Now, the only thing I would say is, like, you generally don't think of this as a power series unless there's like an x in there. Power series we usually think of as a function. So this is maybe not a function of a variable, right? This is a number. This is in fact 2 minus root 2. And if someone asked you if that's a function, you might say no. You needed x in there. And we call A the center. I think being the center is a good name for that. I want to make sure I address the converse of what Jack said, though, too. Certainly true that the ones we'll look at, many of the ones we'll look at today are geometric. We're going to kind of use that as inspiration on our first day jumping off. But the converse is not necessarily true. Is every power series, can we think of every power series as geometric? The answer is just no. Like, actually, there are many interesting series of this form that are not geometric. So we'll encounter lots of those, actually, in this year. I'll give you just one more second. Think about that. Anyone else? One second. So let's return to this question that we just had up here a second ago. Is this really an equality? Is this really true? Does that equal sign truly belong there? So let's just look at how this actually acts visually, maybe. Like I said, the answer is surprisingly yes. None of you seem super shocked, so but you should be. I think it's exciting. Let's take a look at the first couple approximations of this series, the first partial sums, if you will. So here's the function that we want. We claim that this equals 1 over 1 minus x. There's a picture of it. Now, that's a very interesting picture of it. I've zoomed in on what? You see where I am on the function? Yeah, I've zoomed in on the place that I claim that this will be equal. Outside of this limited domain, all bets are off. But inside this domain is the place where we're making this claim, just to make sure we're being clear. So the rest of this function has all sorts of other interesting behavior you might expect from a rational function, but certainly on the interval -1 to 1, that's what it looks like. This is not a very good approximation, but this is what we might call the first order approximation of this function, or the constant approximation. Here's the first two terms. Stop there, right? 1 plus x. We might call that the linear approximation. Or, what else, friends? What else is that called? Look at the picture if you need some inspiration. What is that? Yeah, that's the linear approximation. That's the tangent line. That we have so many different names for this now. It's the first order approximation. It's the tangent line. It's the linearization is the other name we've given it, right? So I want to make sure you understand that this is the discussion we've had this year so far. Stop there. But can't we go further? And with this function, yeah, there's the new concept, the second order approximation. Notice how already the purple graph seems to be, the whole graph seems to be converging at every point to the black graph already, even though we're only 3 terms in. Here's the third order approximation, just showing that it is getting better. There's the fourth order approximation, getting even better still. And I'll take you to, gotta fire up Desmos here too. There we go. So I'm going to pull this up in Desmos. Here's 1 over 1 minus x. And we'll zoom in, just like we said, around this interval of interest from -1 to 1. And let's watch this thing happen. So we'll call this second function g of x. So it's 1, there's the constant approximation, linear approximation, quadratic, cubic approximation, quartic. And actually, this is fun to type all this in, but let's maybe do this a little more quickly. How many terms would you like? How about we just did the 5th order approximation? So there we go. Does that work? Can we write it in just in summation notation? Save ourselves a lot of time. 6, 7. Let's just put the number m there. How many would you like to see? 1,000? Sure. Okay. All right. Now here we go. This is fun. Can I do this really? I want to do it nice and slowly though. Really, really slow. There, that's as slow as it goes. Okay, here we go. It's still way too fast. You know, let's only do 50 terms or something. Well, now it's kind of too slow. I mean, and actually this converges so quickly that it like really stopped being interesting, because like after 10 terms, you don't really gain almost anything by adding an 11th or 12th term. But you see, again, the place this is converging is on the interval -1 to 1. Outside that, all bets are off. But we get something that's so close to really the only convergence we're now seeing is really near -1. Everywhere else it almost looks identical. All right, well, whatever. Well, that's 50 terms, right? Anyway, we're having fun. All right, let's go back. All right, so let's take this power series and let's actually give what function it represents. This is a function. Right? This is now what we're talking about. This is a function that we're speaking of. Give what function it represents, and also using your knowledge of geometric series. Give the interval over which that makes sense to call this the function you named. Right? Give the interval of convergence as well. Is this geometric, by the way?
Yeah.
Yes. You want this one, Max? I'll take it. Whenever you're ready. What do you think? Give us the rule. What's the common ratio here? What's R? Yeah, 3x, right? The common ratio here is 3x. So give me we'll call this f of x if you like. If you give me a rule. And yeah, is the first term 1? Yes, good, okay. We have to be careful about that, but 1 over 1 minus 3x? Yes, that's terrific. Do you want to give me the interval of convergence too, while you're on a roll? That is, where does this actually equal, when do we actually have equality here? We have to insist that x be between what and what? Say it again. -1 and 1? Careful, if x happens to be, 0.8 or something like that, I think what we get here is, for the common ratio, is 3 times 0.8. Is that something bigger than 1? I think it is. So we have to be a little careful there. Yeah, what do we want to insist that that x has to be? I agree, r has to be between negative and positive 1. But what does x have to be between? In order to ensure that r is between negative and positive 1, of course, what? Yeah, between negative 1/3 and 1/3, right? So I think we can say that. That answers the question. We're good. We have identified the function that this is representing, this power series represents this function. And we've identified the interval of convergence. Let's do another one. This one's centered at 2 instead. So what's the common ratio here? Yeah, you can. I might just say negative x minus 2, but absolutely negative x plus 2 if you want to say that. You can. Yeah. What's the first term? Is it still boringly 1 here? Yeah, plug in 0. Okay. So what do we get as this function? 1 over, well, I guess maybe I do want to write negative x plus 2 there. Something. But it would be what? 1 minus or 1 plus x minus 2, I guess. Actually, I guess we could simplify that even more. What would that be? 1 over x minus 1? You have to find a way to write that function. All right, now, interesting question, of course. What's the interval of convergence? How do we figure that? We want to insist that r always be between negative 1 and 1. So what does that mean in terms of x? Are you guys comfortable with inequalities? You might multiply this through by negative 1. What happens then? Yeah, we have to flip the direction of the inequality. And then, what do you do everywhere? Just everywhere, add 2. Yeah? You see how I might reason through? You can do this on the last one too. This is how I might get the interval of convergence from, again, we're only dealing with geometric fashioned things right now. But if we're dealing with something geometric, this is how you might do it. This might be how you get in on that. So on Desmos, how we're going to graph this series, which would be very easy to type in Desmos like I just did, and type this in. We could see it converge. Where would I zoom in? Well, on the interval 1 to 3. We'd watch it converge ever so slightly. Questions before we say anything more there? Are you catching what we're putting down? I mean, we've jumped to another level of abstraction here in terms of functions being these series. Might be unsettling still for some. Okay, well, let's do the other thing. If I gave you this, I mean, on this one actually it would be a little tricky. If I gave you this, could you come up with a power series that it represents? On this one it might be a little tricky, given the fact that this one was centered at 2, but so let's see if we can come up with a power series representation for this kind of normal represented function. And we'll give the interval of convergence too. So maybe we should say what r is. Here r is just x squared. And if you want to write down like what a1 is, I guess you could write that as well. a1 is equal to 2. It looks like. What do you think? You want to take it, Rebecca? You want to write a rule for us? A power series? So you write us a geometric rule that has this as its sum, right? Be the question. Can you have it? We'll give you another minute. Everyone else probably needs a second to think about it too. Yeah, do it. Turn to your neighbor, tell them what you get. And determine the interval of convergence too. Slide. It's just we're going back and forth, right? So what's the first one? How do you write the geometric series? You have it? No? We'll give you another. No. Oh, help each other out here. I think there are a lot of people who don't know what I'm asking maybe. Do you know how to write the rule for a geometric series in general? Well, let's go over here and do that real quick. If someone gives you some geometric series, 5 plus 10 plus 20 plus 40. How do you write the rule for this series? Just in general. What would it be? What's A1? What's the common ratio? 2. And then how do you want to index this? What would you? This is a choice. This is not no right or wrong answer. What would you like to do? I don't know. You want n here? Then what belongs here? 0. Fine. There you go. Now, does that converge? No. But I don't know. Who cares about that right now? We're just asking, do you know how to write the series, the rule for the series? Or you could write it as, we have options. You could write it as n equals 1 to infinity, 5 times 2 to the n minus 1 would be, I think that's kind of our favorite way from pre-comp to write it, you know, a1 times r to the n minus 1. Anything correct is fine though, right? Anything produces this series is fine with us, yeah? So, can you take it? So you're going to start with 0, okay, great. To infinity, sure. Yeah. Now the only other thing that we might do is make sure that, is this really going to be powers of x? Just x? Yeah, it's 2 times x to the 2n, right? So you could write it that way. And now we're convinced. Isn't this a power series? Isn't this going to be of the form something times x to a power, well, something times x to a power? Certainly. Yeah. So I think we're good. What is the interval of convergence here? Let's say what it is. Maybe just even by inspection. How can we keep x squared between -1 and +1? When is this true? It's a little bit of a tricky question, maybe. Maybe just reason with me about it, though. Try some values. What x values seem to work? Say it again. 0 to 1 certainly seems to work. Certainly when you square things. What did you say? Does it work to have negative numbers too? I think it's actually still -1 to 1. Right? Now, how would you get to that? You might be thinking, well, we just need to take the square root everywhere. That's a little problematic, right? Given the -1 here. Well, let's just verify that this, x squared, by the trivial inequality, this already holds, doesn't it? Isn't x squared necessarily always greater than 0, regardless of what your x is, even if x is 50? If x is -100, x squared is always greater than 0. So let's start by just saying that, just by the nature of the expression, x squared is a positive thing, always. Yeah. And now what can you say? Well, now I guess you could take square roots everywhere. You have some experience, perhaps, solving inequalities like this. If I subtract 1 back in pre-comp, or even in this course, how might you do that? You might find the zeros. You might graph it. I don't know how you want to think about this. But that's how we've done it, I think, in this course. We've kind of thought, okay, well, this is by the way, way too much thinking for this one, right? Obviously, you can just kind of do what you just did. But I'd be like, well, I just kind of see it. I know that it's numbers between -1 and 1 will keep us between -1 and 1 for x squared. You know, that's good. That's fine. We'll just write it down. But if you want a deeper analysis, technically, this is like the way we thought about it earlier in this course. You might draw a number line, and then think about where is this negative and positive. And certainly, anywhere in here, you get something negative, right? Okay, which is what we want if we're just all trying, whatever. The point is we're done, okay? You can have a more technical eye on this, but you know, this is maybe too much. Good. Let's do another one. Let's do as many as we can before the bell's gonna ring. Anything. We'll do this one quickly here. This is a little tricky because it's hard to see that this is in the form that we need it to be. Can we rearrange algebraically the bottom to convince ourselves that it's of the form 1 minus r? Can we write it in this form? Sure. What would go in the parentheses? Yeah, we could just write negative x cubed here. Okay, so then we just have as n goes from, we could do 0 again to infinity. What do we get? First term times the common ratio to the n if we're doing 0 here. I think that works. But then you still have to convince me that that's actually a power series. Is that really, and when you multiply it all out, if you start plugging things in, do you really, what you get is something times x to the power plus something times x to the power? It's not obvious that that's true until I write this as a single power of x. So let's do that. And can you do that? It's x to the what? Here, x to the negative, x to the negative x to the three n. Here, let's do negative 1 to the n out front. We'll take care of that first. And then we still have the x. And then we still have this x to the 3n. Is that okay? Can we do that? We're not done yet, though. So I might write this as, finally, n equals 0 to infinity, negative 1 to the n, x to the 3n plus 1, rules of exponents, right? And now have we written this as, this is certainly true, that no matter what n value you plug in, like say you plug in n equals 50, well this will be some constant. In our case, it'll just be either a negative or a positive 1. If n is 50, then it'll be 1 times x to 151. Perfect, right? No matter what n I plug in, I will get something times x to some positive integer power, right? So I think we're good there. And the interval of convergence, when is x cubed? Between, this one's also negative 1 to 1, isn't it? Okay, more